Greetings, it's Paul Bamberg welcoming you to the preview video for Class 6 in Mathematics S-322. Two topics today. The first one, uniform continuity, very important and one with which you might not be familiar at all. The second one will be familiar if you have taught AP Calculus, namely limits, but with Ross's definition of continuity in terms of sequences, I'm going to show you a different definition from the one you're probably familiar with. So let's get going with uniform continuity. I want to contrast continuity with uniform continuity. Turns out the difference is in the order of the quantifiers, and the best way of thinking of this goes over quite well with students, is that two people are playing a game. One person is challenging the other to prove that a certain function is either continuous or uniformly continuous. So let's first think about how the continuity game is played. If we're playing the continuity game, we start by agreeing on some value y in the domain of the function before we ever think about epsilons and deltas. For uniform continuity, we're going to pick an epsilon before selecting y, but for continuity, we first choose the y in the domain. Then I challenge you with some positive epsilon, presumably rather small. You respond to my challenge by selecting a positive delta, and you win, proving that the function is continuous at y. If for any x that's in the domain of the function, with the property that the difference between x and y is less than your delta, the function values f of x and f of y differ by less than epsilon. If you can do this for every y in the domain, you say the function's continuous. How could you have something different? Well, watch carefully. Here's uniform continuity. First, I challenge you with an epsilon. I say, I want the function values at two nearby points to be within 1/1000th of one another. You respond with a one-size-fits-all delta. You say, for example, fine, make x and y be within 1/1,000,000th of one another, and we're fine. And how do we test whether you've won or not? For every x and y in the domain, with the property that x and y differ by less than delta, we have to have the difference between f of x and f of y less in magnitude than epsilon. You've got to look at some examples to see where the difference lies. First example, let the set be the non-negative real numbers, 0 to infinity. And by the way, this set is both open and closed at its upper end, so it's correct to use either a square bracket or a round bracket here. The squaring function is clearly continuous on this interval. That's not hard to show. The surprise is that it's not uniformly continuous. I don't want to write out the details in this preview, but basically what goes wrong is if I say, I want you to make x squared differ from y squared by less than 1/1000th, no matter how small a delta you pick, no matter how small the difference between x and y has to be, I can pick a couple of really enormous numbers, so the difference between the squares of these numbers is quite large. I don't need an infinite interval in order to do this. Let's look at the open interval from 0 to 1 and the 1 over x function. This function is continuous at every point in that interval, but it's not uniformly continuous. Here the problem is if you say, oh, just make x and y be within 1/1000th of one another, I can choose a couple of tiny values of x and y, so the difference between their reciprocals is quite large. However, if we stay away from these two counterexamples by insisting that the interval be closed, which was not the case in the second example, and bounded, which was not the case in the first example, then continuity implies uniform continuity. Very important result. However, you may not have proved it in your AP Calculus course, and the reason is the proof, which is actually fairly simple, requires the Bolzano-Weierstrass theorem, which is not. Now here's a theorem that I didn't know before I started teaching this course, but I think it's really quite elegant. Remember our definition of continuity of a function. If a function's continuous at some point in its domain, and you've got some sequence of points in the domain that converges to that little s, then the sequence of function values converges to f of s. Suppose, on the other hand, this sequence s sub n is merely known to be Cauchy. In that case, we know that it converges, but we don't know what it converges to. The interesting result, which we will prove, is that if we want the sequence of function values also to be Cauchy, then we require not merely that f be continuous, but that it be uniformly continuous. To summarize, a continuous function maps convergent sequences into convergent sequences. A uniformly continuous function maps Cauchy sequences into Cauchy sequences. I kind of like that. Okay, so on a closed interval, we don't have any real problems. On an open interval, as you've seen, a function can be continuous without being uniformly continuous. However, frequently we can deal very nicely with an open interval by extending the function. I'll use Ross's notation by putting an overline on the f. And the way we define this extension is that we define the value at the endpoint a or b so that the function is continuous there. Now the function is continuous on the closed interval from a to b. It's uniformly continuous on the closed interval from a to b, and it's uniformly continuous on the subinterval from a to b. This sounds esoteric, but there's an example you've probably used in your own teaching. The function that's defined by sine x over x as long as x is positive. Every student will say, the value of this function is 1 at x equals 0. Everyone knows that. But this formula doesn't work at x equals 0. The function that is equal to 1 when the argument is 0 is the extended function defined to make this function continuous at that point. If we're willing to jump ahead and use a little bit of calculus, there's a nice alternative. If a function is differentiable on an open interval and the derivative is bounded on that open interval, then we can be sure that the function is not merely continuous, but uniformly continuous. Well, you might not have expected that getting back to just talking about limits would come as a relief, but here's a slightly more familiar topic, limit, and a slightly unfamiliar definition. This is based on sequences, and I think it's a splendid definition. S is some subset of the real numbers. F is a function defined on that domain S, and A and capital L can be real numbers. Either can also be plus infinity or minus infinity. And we have the concept that the limit of f is equal to L as x approaches A. But what do we mean A super S? What this means is consider any sequence in S, x sub n, whose limit is A, then the limit of the sequence of function values is L. So when we talk about x approaches A, students often wonder exactly how does x approach A, and I think most students imagine that x approaches A through some uncountably infinite sequence. When x approaches 0, it goes through all the real numbers as we get down to 0. This says, as long as we're willing to consider an arbitrary sequence, we only need a sequence of values. So that's Ross's definition, and with this definition, we can use all the results we already know about continuity in sequences. Here's the more conventional definition of limit, with which you are very likely familiar. We've got a function defined on some set of the real numbers. We have a point at which we're taking the limit, a real number, not necessarily in S, but in the closure of S. It can be achieved as the limit of a sequence in S, and the limit L is a real number. This definition does not work when S is plus or minus infinity or when L is plus or minus infinity. Ross's definition does. Then, the limit as x approaches a of the function f has the value L means this. I challenge you with some positive epsilon. You respond with some positive delta, and you win if for any s in the domain that differs from the purported limit a by less than delta, the difference between the function value f of x and the limit capital L is less in absolute value than epsilon. When both these definitions work, they're equivalent, but we'll find the first one much easier to work with in general. When we finally get around to doing calculus, we'll need theorems about limits in order to prove differentiation rules. For these theorems, the point at which we're taking the limit can be plus or minus infinity. So we can be talking about limits at infinity, but the limit itself has to be finite. And we've got two functions, f1 and f2. They approach limits L1 and L2, respectively. Then, using our theorems about continuity, it will be quite easy to prove the following. The limit of the sum of the functions is the sum of the limits. The limit of the product of the functions is the product of the limits. And the limit of the quotient of the functions is the quotient of the limit, provided we avoid dividing by 0. We say the limit L2 has to be non-zero, and the function value has to be different from 0 for S in the domain. For calculus, we're also going to need the composition of functions when we get around to the chain rule. And in this case, the existence of the limit involves some rather subtle conditions. Let's suppose that we know that the function f has the limit L as x approaches a. Then, if we take g of f of x, the composition of g and f, the limit of that composition function is going to be g of L, provided all the following things are true. G has to be defined on the image of the domain of f. It has to be defined on the set of function values that you get by applying x to s. Furthermore, it has to be applied to L. Say, isn't that obvious? Isn't L in this set? No, it isn't. L just has to be a limit point of this set. So the set might include a half, a third, a fourth, a fifth, but only positive numbers. L itself could be 0. And finally, G has to be not just defined at L, it has to be continuous there. As a final topic, let's think about one-sided limits. When you write limit as x approaches a plus of f of x, what you mean is that x is approaching a from above. And sometimes such limits exist, even though the limit as x approaches a does not exist, because f does weird things for negative numbers. If we're using Ross's definition, all we have to do is say we're going to choose this set capital S to include only values that are larger than A. If we want the conventional definition, we consider only values of x that are greater than A. In other words, this limit has the specified value if for any x between A and A plus delta, the difference between f of x and L has absolute value less than epsilon, and we don't worry about x's that are less than A. It's obvious, and also fairly easy to prove, that if the limit from above is L and the limit from below is L, then the limit is L, and conversely. And we're finished with this topic, except we got a whole lot of things to prove, and we need to get some skill in calculating limits. Both those things will be done in class.